Okay, so this is an example of calculating the electric field in a two-dimensional scenario. So what we have is we have two charges, charge 1, charge 2. Charge 1 is negative 2.4 microcoulombs, and charge 2 is 1.7 microcoulombs. We're going to assume that each one of these squares is 1 meter. So what we're going to do is we need to figure out what the vectors are associated with going from charge 1 to point A and from charge 2 to point A. Because what's going to happen is that the direction of the vectors is going to be along the line connecting them. So these are the lines connecting the points. Now, because we assume that there's a positive test charge at A, the electric field is going to be pointing upward to the left for this one, because the positive and negative charges attract each other. Whereas here, this is a positive charge, so this positive charge repels, the positive test charge is repelled by the actual positive charge. So in this case, the vector is going to go up in that direction. So the first thing to do is to figure out what these vectors are. The position vector from the charge to the point in space. So you just take y2, actually it's x comma y, so it's x2 minus x1, 4 minus negative 5, and then y is 3 minus 6. So you get this vector 9 comma negative 3, which means you go 9 units in this direction and negative 3 in that direction. Likewise here, we can see what it is. It's 1, 2, 3, 4, 5, 5 in the I direction, and then upward 1, 2, 3, 4, 5, 6. Again, you can use the coordinates to come up with those vectors. So those, I don't have them showing as vectors, but I need to do that. So these are vectors. That's a vector. And it's from charge 1 to point A, from charge 2 to point A. Okay, now from a vector standpoint, the equation for the electric field vector is k times q, and there's no absolute value here, times the position vector. I'm using this other terminology with a little hat. So r1a divided by, this is divided by the magnitude of r1a, because this makes it into a unit vector. But this one is divided by the magnitude squared, because that's what the equation for electric field is. So you actually end up with r cubed in the denominator, but it's okay because we have this r vector in the numerator. So we need the charge, which we have, q1. We have the vector r1a, so we just need to figure out what the magnitude of r1a is. So you take the x component squared plus the y component squared, take the square root, Pythagorean theorem. Now I didn't put the negative sign here because when you square it, it goes out anyway, so I could possibly put a negative in there. You get the same answer, same way. Well, these are both positive, so I don't have to worry about it. So we see from charge 1 to point A is 9.49 meters, and from charge 2 to point A is 7.81 meters. So now we just plug it in. So here's Coulomb's constant. Here's the charge. Charge 1 is negative 2.4 times 10 to the minus 6 coulombs. So we convert micro into scientific notation, then multiplied by the vector r1a and divide by the magnitude cubed. And we end up with this vector. So this is the vector that says what is the electric field at A due to charge 1. And if we look at this, here we have a negative x and a positive y. So if we go back to our original thing, what we said was that the electric field vector is in this direction. because of the opposite charge between the charge and the positive test charge. So you can see it's going to be negative something and positive y, and the x part should be bigger than the y part. So qualitatively this makes sense. Now you do the same thing here. So K Coulomb's constant, positive 1.7 times 10 to the minus 6, R2A divided by the magnitude of R2A cubed, and you end up with that, 160 I plus 192J. So they're both positive. So let's go see if that makes sense. So if we go, this is the direction of the electric field, because this is negative, this is positive, the test charge is positive, they're going to repel each other, so it's going to go in the direction that you would get if you drew a line between the 2 points, the center of the charge and the point in space. So it's going to be positive x, positive y. It looks like the y part should be slightly bigger than the x part. Let's see if that's the case. Yeah, the y part is slightly bigger than the x part. Then you use the principle of superposition. So the total electric field at A is the sum of the two electric fields. One from charge 1, one from charge 2. So we just add the two vectors together. So you add the x components together, you add the y components together, and that's your answer. And the units are newtons per coulomb. Now let's just look at, here's a diagram with the vectors drawn in. So this vector here from A pointing towards charge 1 is EA1, so that's that vector. Then you have EA2, which is the electric field due to charge 2. It's pointing that way. What I did was I copied this vector EA2 over to here so that I could do a tip to tail graphical representation here. So then we go from the tail of vector 1 to the tip of vector 2. That gives us the resultant vector, which is this total vector. And it says that the x component should be negative and the y component should be positive, and that the x component should be significantly smaller than the y component. And we look back here at the numbers and you see that's true. Negative x, positive y. This is much smaller than that. So that is it.